This is the A.E. Staley Sagamore cogeneration facility, which will be capable of supplying 190,000 pounds an hour of steam at 685 psig and 750 degrees Fahrenheit. The plant will be capable of developing at least 7,415 kW at full throttle flow.
Okay, now you see a truck pulling in to unload its load of coal on top of the Grizzly. Now you're seeing the truck being dumped by a hydraulic cylinder.
The boiler is designed to fire all of the specified coals. It is noted, however, that it will be necessary to add a dry scrubber system for future firing of high sulfur coal.
The coal you see left on top of the Grizzly will be shoveled in by the use of the Bobcat by one of the operators, distributed over the Grizzly so it'll go ahead and fall through. This Grizzly is divided up into openings that's approximately 3 inches wide and 5 inches long.
The truck receiving hopper, located directly below the Grizzly, is designed to receive 40 tons of coal in 2 pyramidal hoppers. At the base of each pyramidal hopper is a vibratory pan feeder, which conveys the coal at 50 tons per hour to a 50 ton per hour single roll Williams crusher. Tramp iron removal is provided for by this magnetic separator. The coal then discharges down to this 50 ton an hour single roll crusher and discharges from the crusher and is loaded into the base of a 50 ton per hour bucket elevator. The unloading system is therefore completely redundant and gives you a combined unloading rate of 100 tons per hour. The coal is then stored in a 2,000 ton concrete coal storage silo. Here we see the bottom side of the silo with its cutoff gate. The coal is reclaimed from the silo by means of a screw conveyor, which will then load one of the 2 bucket elevators shown earlier at a rate of 50 tons per hour. Here we see the outside of the 2,000 ton storage silo and its bucket elevator. The coal is then conveyed to one of 2 day bins in the plant by the use of this bucket elevator and a transfer screw conveyor. There is also a wet dust suppression system which controls the dust at the pan feeder discharge and around the coal crusher.
Okay, what we have here is a storage bunker for the pulverizers. We have one for each pulverizer that holds approximately 200 tons of coal or a day's supply of coal. The coal discharges out of the bottom of the bunker valve down through this slide gate, which is called the bunker slide gate, travels on down through this conduit and discharges directly on top of the belt located inside this stock gravimetric feeder. This valve has to be open before the equipment will run and deliver coal down the conduit and into the feeder. Once the coal enters the feeder, it travels down the length of it by way of the belt, all the way down to the end of it, where it discharges, drops off the end of the belt, travels down through the bottom into a chute that leads directly into the coal pulverizer. There's a coal on belt indicator inside the mill, inside the feeder, resembles a flag. The coal has to be present on the belt to make this switch up, which will allow the feeder and the rest of the equipment to operate.
What we are now looking at as a window at the end of the stock gravimetric feeder, and through it we can see the coal containing upwards to 8% moisture as it discharges directly down into the Williams pulverizer.
What we're looking at now is a digital display on the stock gravimetric feeder. The top figure you see there is the pounds of coal they have run through this since it was last reset. It's showing right now 155,000 pounds, and they reset this every night at midnight. Below on the second figure you see there is the feed rate. Right now it's feeding at just over 5 tons per hour.
The new plant is located directly adjacent to the existing boiler house and serves as the primary source for the plant's electrical and steam requirements.
The fan and the feed flowing down the feed chute. This pipe is connected with the discharge of the stock gravimetric feeder. Comes down through this pipe and down into the mill. The noise you're hearing is the coal coming from inside, that's flowing inside the conduit. Okay, the coal then enters the grinding chamber inside the mill where it's then ground up.
Mill bottom discharge permits continuous removal of iron pyrites, slate, and in particular tramp metal, simultaneously with the grinding operation. Some product beneficiation is possible by the removal of the hardest to grind materials that accumulate at the bottom of the semi-fluid bed at the base of the mill. Removal of pyrites and tramp metal and slag producing impurities are possible by periodic dumping as shown here.
We're standing underneath the gearbox now, and as you can see, the mill is in operation. There's absolutely no noise coming from the mill itself. The noise you are hearing is from the gearbox. this is our automatic lubrication unit. We have a pneumatically operated pump here. We get our air supply that's filtered, it's regulated, and then it's lubricated. The air goes through the solenoid valve, which can be manually operated, or usually it's operated through the computer. And once the solenoid valve is activated, the air comes all around and into the pump. Once the pump has been actuated, the grease flows from the bottom of the drum up through the pump, out this hydraulic hose, and then to a pressure gauge here, which also has a ruptured disc in it. As you can see from the grease stains, this disc has been ruptured. This is primarily due to the air pressure being turned too high. And the grease then leaves here, goes up through a strainer. As you can see, the grease is just automatically actuated from the computer, travels through the strainer, on up, and into our primary distribution block. On the very first block here, we have a cycle switch. This lets the computer know that the grease pump has cycled, and it counts the number of strokes. Then the grease, it continues on through each individual block, distributing grease throughout the system. The primary line here goes into the inside of the pulverizer. The grease travels through a broken line indicator switch here. When as the grease is pumped through, there's a pin in here that actuates this limit switch. Now this limit switch has to be maintained for several seconds, otherwise we get an indication to our computer that we have a broken line. Okay, as you can see, the pin is still extruded and it has the micro switch made. The grease then travels on up through into the interior of the mill through the air seal chamber. This is where the air seal assembly begins. This is a plant air supply coming to us. We have to have a minimum of 15 pounds per square inch. It goes through a solenoid valve, which is controlled by the Williams computer, leaves there, goes on over to a pressure regulator. Once it leaves the pressure regulator, it comes up through a pressure switch. Now this switch has to maintain a certain amount of pressure, otherwise our computer will shut the system down. Right now it looks like the switch is set for approximately 12 to 13 pounds. The air then leaves here, travels up the 1.5 inch pipe there, and into our air seal chamber in the mill. Okay, once the air supply leaves the pressure switch, continues on up this 1.5 inch line, right on around, and it goes up, it branches straight in to the inside of the mill. Lube system, our lube system, puts the grease through this 1/2 inch stainless steel tubing directly inside the middle of the air stream. Okay, our primary air supply for this DF mill enters by way of this insulated duct here. Comes inside the wind box circles the entire mill and comes through its inlets throughout the circumference of the mill. The air then sweeps inside the grinding chamber, flows up through, lifting material with it, up through to the spinner separator, where the material is classified by the speed of the spinner separator. When the material is small enough, it then leaves the classifier, exits out the top, and flows through a conduit across through the exhauster and then on into the boiler itself.
The coal and air come through this pipe from the pulverizer down up into the exhaust fan. The coal and air then come out of the exhauster past the temperature probe into the splitter valve. The splitter valve distributes the coal to the two pipes above it through the burner safety shutoff valves. The coal is then transported out through these pipes to the burners.
This is the coal inlet pipe. The coal and primary air comes down the pipe and enters the burner in a swirling motion and travels into the furnace. Coal comes in at a 2.3 to 1 air to coal ratio. The air transports the coal and delivers it into the combustion zone, where it mixes with secondary air, which comes in from above through a large area called the wind box. The air and coal mixture mixed in the furnace zone. They're ignited by the igniter, which is fed to this igniter tube with natural gas. At a stable load of approximately 40%, the igniter is taken out of service and the coal is self-sustaining. When the coal is self-sustaining, the excess air to the unit is approximately 4 to 4.5%. Back in here is a main flame scanner supplied by Forney Engineering. Detects the coal flame with or without an igniter flame to support it. This damper drive at the top is for a sleeve damper, which controls the amount of secondary air allowed to the air register and eventually delivered to the furnace zone. This control panel here is mostly for local readings. It measures the differential from the wind box, which is the supply air, to the furnace. The box below it is the main transformer for the gas ignition.
This then is the Foster Wheeler SPEC standard SF type steam generator. The boiler is capable of supplying 190,000 pounds per hour of steam at 685 psig and 750 degrees Fahrenheit, and developing at least 7,415 kilowatts per hour at full throttle flow.
Here we have the Provox consoles, which will give a graphic display of everything that's going on concerning the boiler, pulverizers, steam flow. Basically, it monitors everything. We have two different screens here so they can have two operators operating the system simultaneously.
Everyone sit down, Gary.
graphics you're looking at now is the bag house. You can tell from this graphics display here what the bag house is doing. At the moment, everything's in automatic. It's got a differential pressure reading across the bags, inlet temperature, and we'll also have an outlet temperature.
Go ahead. This is the Williams System 200 control system for the Lafayette A.E. Staley project. The control panel, as you're looking at it, as you look at the meters, first meter shows pulverizer speed, second meter shows spinner separator speed, third meter shows boiler demand, fourth meter shows differential pressure, fifth meter shows feeder command, sixth meter shows pulverizer temperature, system airflow, horsepower, manual speed pots for the spinner, pulverizer, feeder, computer reset, system test points, and the handheld data terminal.
Show me that.
This terminal allows you to interrogate the system or change setup parameters. If you want to monitor a function, you press the monitor key. Monitor number 1 would be demand signal coming to the Williams computer. That demand signal is sitting at 58%.
Can you show me, those are setup values or monitors?
This is a monitor value.
Okay, how about monitoring the delta P? Items 2, I believe.
Item 2, the actual differential pressure is 4.6 inches.
Okay, and item 3
Is
4.6.
ideal. This is what the pulverizer computer says it should be running at, and it is exactly on. You can also change setup parameters
All right, would you show us that?
by pressing setup.
All right.
Number 1 is the minimum speed, mill speed of the system. Press setup again. That increments me to the second table, which is maximum mill speed, which is 100%. I can change that value by decrementing or increasing.
But none of those values are stored.
If I hit the store key,
All right.
it asks me for a password.
In other words, you have to have a qualified password to get into this system. You have to have the password.
The only way you can enter the password is hit the star, the password, and the star again. Then your password is valid. Once you've changed your setup parameter to where you want it, press your star again, it turns your password back off.
That's so unqualified personnel cannot make changes. Okay, would you show us what this leads into, the computers that are on the inside?
If I press the annunciator reset, it will clear the annunciator back to normal and say Williams DF Mill. On the internals of the Williams System 200 control system, you will find a 3-board set of computers. The board on your right of the cabinet with the 8 large black modules on it are your analog output. These analog outputs control the spinner speed, feeder speed, and mill speed at this time. You then also have 5 spare control signals for other devices in the plant if need be. Upper board on your left is the brains of the control system. This computer is a 6809-based microprocessor system. It's an 8-bit microprocessor with 16-bit math capabilities.
Show me the chips, please.
Okay. All the memory of the system relies on EEPROM and E²PROM. This allows the system not to have batteries. If the power goes down, you do not lose memory where you normally do in most other systems. The memory is burned-in memory. We can also change the program by adding an HP71 and using the Williams Sight Logic by plugging into this upper plug, J3. The bottom board of the 3-board set is your discrete I/O on this side of the board and your analog inputs on this side of the board. Your analog inputs are differential pressure, demand, 3 is a spare, 4 is pulverizer current, 5 is temperature, 6 is airflow, 7 and 8 are spares. These are looking at 4 to 20 milliamp signals coming from the field devices. The discretes are discrete outputs, discrete inputs. Those talk to the solid-state relay cards on the far right of the cabinet. These are the discrete I/O modules. These are the solid-state relays that talk to the motor starters and such in the field. These are the on and off controllers. Far right are inputs. The black modules are outputs. The system is set up to handle 48 I/O.